I will start with a brief project overview, telling some main points that we are doing in IDEAL. And then I will concentrate in a bit more detail into decentralized automation architecture and congestion management algorithms that we are developing in this project. As we all know, the planning and operation of electricity networks is becoming more complex when we add distributed energy resources, such as DG units, to distribution networks. At the same time, we are facing demands to use the networks as efficiently as possible and to guarantee the continuity of electricity supply. In IDEAL project, we are developing, implementing and demonstrating control and planning methods for active networks to be able to fulfill these demands. And we are also including possibilities to utilize also small-scale distributed energy resources through aggregator concept. The main objectives in the project are the following. We are developing an advanced distribution network automation system and functionality to use on this automation system. Then we are demonstrating this developed automation system and control functions first in real-time, using real-time simulations, and after that also in 3 separate real distribution networks. The demonstration sites are located in Italy, Spain and Denmark. In addition to developing these control methods, we are also developing planning tools, because it's not enough to develop control methods, but we need to also evaluate the benefits and costs of these methods so that DSOs will really know what they get if they take these methods into real distribution network use. In IDEAL project, we are dividing the breakthroughs that we are achieving in 4 different categories. The blue ones are concept breakthroughs that we have defined at the beginning of the project. Then we have breakthroughs related to monitoring. Those are the yellow ones. We are monitoring the medium voltage and low voltage networks, the state of the whole network, and this data can be used by the DSOs, but also by the TSOs. And then we have the green breakthrough cluster that has the control functions in it. There are planning functions, fault location isolation, supply restoration functions, congestion management functions, and functions related to microgrid control. The project is divided in 7 VPs, and the VP7 combines all these other VPs that have developed the methods together in these demonstrations in the real networks and in the real-time simulations. Okay, then I will briefly talk about the decentralized automation architecture that we are proposing in IDEAL. At present, distribution system operators are controlling and monitoring the network only from the control center level. So all the data that is monitored is first transferred to the control center. The control decisions are made at the control center level, and then the data is transferred to the controllable devices. This is fine for the current state, where we don't have that many measurements from the distribution networks and we are not able to control many resources. But when we get more data from the networks and we have more controllable resources, the amount of data transfer and the complexity of the control functions would become too large. And therefore we are proposing a decentralized architecture that consists of adding substation automation units both to primary substations and to secondary substations. The primary substation automation units will be responsible of monitoring and controlling the medium voltage network, and the secondary substation automation units will be responsible for monitoring and controlling of the low voltage networks. And only the necessary data is transferred between these different substation automation units and the control center. So not all the data need to be transferred throughout the whole network. As an example, I will show the real-time monitoring and state estimation use case. We are utilizing smart meter data to monitor the network state. And the smart meter data is transferred from the meters to the secondary substation automation unit. Because the data is incomplete and uncertain, we utilize a state estimation algorithm to know the state of the whole low voltage network. Based on this state estimation data, we can then make some control decisions if they are needed. Only the necessary data is transferred to the primary substation automation unit, and in this state estimation use case, the necessary data is only the sum of real and reactive power transfers through the distribution transformer. So the needed data transfer is much smaller than if we would transfer all the smart meter data to the primary substation automation unit or to the control center level. Then I will talk about these congestion management functionalities that we are developing. I won't be able to cover all the control functions developed in this small time scale, but I will now concentrate on this one topic. The aim of congestion management algorithms is to mitigate congestions in the network. They can be voltage problems, DC units increase the network voltage, and with the current planning principles, voltage rise often gets too large. And also overloading of feeders or transformers is possible, and the algorithm will take also that into account. And the secondary objective of the algorithm is to optimize the network state. But the most important thing is to mitigate these congestions and to increase the hosting capacity of the network. We have divided the control into secondary and then tertiary parts. The secondary control is operating in real time, and its job is to make sure that the network is always at an acceptable state, and after that optimize the network state. It uses state estimation data to determine the control actions, and these secondary controllers are located at the primary and secondary substation automation units, and the control either the MV or the LV network, depending on where the control is located at. It operates through changing the set points of primary controllers that can be, for instance, the automatic voltage control relays of the transformer OLTCs or the voltage controllers of DC units. And it has no connection to the marketplace, so it operates directly when it's needed. Then we have the tertiary controller that operates on the control center level. Its control actions are based on forecasts for a longer time period, and it has several parts. It has a network reconfiguration algorithm that calculates the optimal network switching state for the next 24 hours, and it is also responsible for interactions between the TSO and the marketplace. It doesn't control the distributed energy resources directly, but it utilizes the marketplace for this control. This picture shows the architecture of the whole congestion management functionality. I will not go through it in detail, the whole picture, but you can see that we have functions operating in different time scales. The real-time functions need to be fast because they are also responsible of keeping the network at an acceptable state. So in the real-time part, we have the secondary voltage control that operates through changing the primary control set points, and it operates based on state estimation results. Then we have an intra-hour part that is optimizing the control parameters of the real-time control based on short-term forecasts, and the day-ahead part that is responsible of the network reconfiguration and also buying the flexibility products from the marketplace. The aim is to use the control in such a way that we wouldn't need to utilize generation curtailment or load control at the secondary voltage control. So the tertiary control is aiming to be able to buy these flexibility products from the market such that we will never need this emergency control in the secondary voltage control. But we will use it if it's necessary. It should be noted that when this ideal congestion management is implemented in a real network, we don't need to implement the whole thing at once. So we can, for instance, implement only the real-time secondary voltage control at the first stage to enable connection of DC unit to a certain network. And then we can add the other functionalities later on if we need it. The structure of the secondary control is shown in the picture. So as I previously said, the power control algorithm located at the primary substation automation units is responsible of controlling the medium voltage network. So it sends set points only to resources connected to the medium voltage network, and the secondary substation automation unit power control algorithm controls the low voltage network. The real-time control consists of these the power control algorithms that are really mitigating the that are calculating an optimal state for the network and mitigating the congestions. And then we have added a BOT unit that is used to prevent hunting of transformer OLTCs if there is a tap changer also at the distribution transformer. And the secondary voltage control is based on an optimizing algorithm, and it has several objectives. It tries to minimize the losses, curtail generation, amount of load control, number of tap changer operations, and the voltage variation from a reference point. And it takes the network constraints into account. At the end, I will show a short example case. This is a simulation done in PSCAD and MATLAB. And the network is in the figure. It has two feeders, medium voltage feeders, and the other feeder has 3 generators and the other only load. And we first increase the generation and then decrease it one by one. This is how the node voltages would look like if we wouldn't have the secondary control there. As you can see, the voltage rise is quite large. This is not acceptable. So in this case, it would be possible to reinforce the network. We would need to build about 20 kilometers of new line. So this would be quite expensive in the example case. We could also utilize the secondary voltage control. As you can see at the uppermost figure, it is able to restore the voltages always between the voltage limits that are set in this example case plus minus 5%. And it utilizes the transformer tap changer and the real and reactive powers of the DC units to do this. The change in curtail generation is quite large. This figure has been done by calculating the load flows throughout the whole year, and if we use the currently used unit power factor control algorithm, we will end up curtailing almost half of the generation in this example case. With the secondary control, we curtail 2%. So the change is quite large. Thank you.